All right, fellas, here to finish up the notes from today. One class, you're already past this, so you can just enjoy the ride here. So for the other class, we stopped with, and sorry, I'm out of breath, of course, I'm very out of shape. So for the inverse of a statement, right, we have if not P, then not Q. So basically, the inverse just means you negate each statement. So if two angles are not congruent, then they do not have the same measure. Okay? Then, last but not least, if not Q, then not P. So if two angles do not have the same measure, then they are not congruent. So again, I've just switched and negated them. Okay? So two statements that have the same truth value are called logically equivalent. Okay? You're going to fill this blank and this blank in with that. So a conditional and its contrapositive are always logically equivalent. A converse and the inverse are always logically equivalent. So if a conditional is true, the contrapositive is true. If the conditional is false, the contrapositive is false. If the converse is false, the inverse is false. If the converse is true, the inverse is true. Okay? Now, in this example that I gave above in the table, all these statements are true. Okay? And that could be the case, but it's not always the case, right? But the conditional and the contrapositive will always have the same truth value. The converse and the inverse will always have the same truth value, which means, which another way to say has the same truth value is logically equivalent. Okay? So if we want to do an example, write the related conditionals and find the truth values. Okay? So the conditional is this. If a number is divisible by 4, then it is divisible by 2. The converse means we switch them. Okay? And this is true, right? A number divisible by 4 is divisible by 2. If a number is divisible by 2, then it is divisible by 4. Okay, this is false. Okay? And remember, to show that a conditional is false, we give a counterexample. So 2 is a counterexample. 2 is divisible by 4, but it is not 2 is divisible by 2, but it is not divisible by 4. Okay? So that's false. So, again, since the conditional is true, the contrapositive will have to be true. Okay? Since the converse is false, the inverse will have to be false. So the inverse means we just negate the original conditional. So if a number is not divisible by 4, then it is not divisible by 2. Okay? So again, we know this is false since the converse was false. So a number is not divisible by 4, then it's not divisible by 2. Well, that's obviously not true. Okay? 2 is not divisible by, counterexample again, 2, right? 2 is not divisible by 4, but it is divisible by 2. So that's not true. The contrapositive, now we're going to switch and negate it. Okay? We're going to switch and negate the original conditional. So if a number is not divisible by 2, then it is not divisible by 4. Okay? This makes sense. This is true. Obviously, it's true because the conditional was true. But we know that if a number is not even, it can't be divisible by 4. Okay? That's basically what not divisible by 2 means, that it's not even. Okay? Okay, there's an extra example here. We're not going to do that too much. We don't have enough time. Okay, so what is a biconditional? That's the whole point. We came all this way just for that. So when a conditional statement and its converse are both true, the two statements can be combined to make a biconditional. Okay, we use the phrase if and only if to express a biconditional, okay? And we abbreviate it using IFF. So if we said P if and only if Q, it's a combination, right? A biconditional means two conditionals. Okay? So it's a conditional, if P then Q, and the converse, if Q then P, okay? So it's two conditionals, the original conditional and the converse, okay? That's it. It's two conditionals put together. So a biconditional is really an and statement between two conditionals, okay? It's really what it is. Okay, the symbol for a biconditional we'll see in a minute. Okay, so how do we parse this? So first, if we're given a conditional statement, right, we can write the converse and the biconditional. So a conditional statement, if an angle is a right angle, then it has a measure of 90 degrees. The converse means we just switch the hypothesis and conclusion. So if an angle has a measure of 90 degrees, then it is a right angle. Okay? That's the converse. Okay? Now, as a biconditional just means that we rewrite an angle is a right angle if and only if it has a measure of 90 degrees. Okay? So, basically we take two conditionals, we get rid of the if then, and we put an if and only if instead. Okay? Now, for this one, right, this next one, they give us the converse, so we have to find the conditional. Again, the converse means they just switched the hypothesis and conclusion. So, this is the hypothesis, this is the conclusion. So now, the original conditional must have been if a shape has exactly 3 sides, then the shape is a triangle. Okay. Now, again, to write the biconditional, a shape is a triangle. I'm going to use the abbreviation if. That means if and only if it has exactly 3 sides. Okay. Now we want to write a biconditional, okay? Now, since we've taken a conditional and a converse, and we've written a biconditional, we want to write the biconditional, okay, as 2 conditionals, okay? So, we're going to split this up. So, we're given x is greater than 2 if and only if x is positive, okay? So, we break that down. If x is greater than 2, then x is positive. That's true, okay? So again, we're just taking the conditional, or we're taking the biconditional, we're breaking it up into its conditional and the converse, okay? So how did I know that that was the conditional? Well, I know it's going to be if this first part here, then this second part, okay? That's how it works out. Now, the converse of this is if x is positive, then x is greater than 2. This is false, okay? It's false because a counterexample can be given, right? So 1 is a counterexample, okay? False. The counterexample is 1, okay? Okay. So the biconditional is false, and it gave a counterexample as to why. Okay? So, really, to find out if a biconditional is true or false, you've got to split it up. Okay? The symbol for a biconditional is a double arrow. Okay? Here's a truth table. So, true, true, false, false, true, false, true, false. So, a biconditional is only true when both P and Q have the same truth value, okay? So true only if and only if true is true. False if and only if false is true, okay? So, honestly, I'm going to stop there because I'm really not concerned too much about the truth tables. But what I really want you to get is this. A biconditional is a conditional and its converse. The words if and only if tell you that you have a biconditional, okay? A biconditional is a combination of if P then Q and if Q then P, for example, okay? Now, remember, the converse means you just switch the hypothesis and conclusion, okay? To write a biconditional, all you have to do is combine the conditional, okay? The hypothesis and conclusion of the conditional joined by if and only if, okay? And to find out if a biconditional is true or false, then we have to break it down and we have to see we have to see whether one of the statements is false. Okay? So, what I mean by that is if, actually, let me put it this way. We know this biconditional is false. Okay. Since I gave a counterexample to show that one of these conditionals is false. Okay. Now, as far as the truth table goes, honestly, you don't have to worry about that at all. Okay, I'm not going to go down that rabbit hole. All right? Okay, so anyways, that's all I got for you today. Make sure to take down these notes. You can omit the truth table part. Okay? You don't have to do that. I don't. All right. Okay, so make sure, take these notes down. Make sure to submit them on Google Classroom. Okay? All right, guys, have a wonderful